So I might thank first of all, I might thank the organizers -1 to give me the opportunity of telling the story of automata with some new insights. So what is automata theory is about states, transitions. Sometimes you have only a letter if your automata are Boolean, as we call. Sometimes you have an input letter and a coefficient. And of course, there are two schools from automata. The automata theory was launched in a very general framework by Eilenberg, who was also one of the founders, one of the forefathers of category theory. And he liked this very much. He interacted with Schützenberger also. And his first launching with non-commutative coefficients. But after, it resulted in two schools, the schools of transducers. I will explain what it is. And the school with commutative coefficients. You can take a semiring and you have rational functions. And rational expressions. Very classical theory of rational expression. And if you are in a field, you can pilot with this rational calculus the Sweedler's duals. Because there was a belief I encountered many times, but now maybe it is overcome, but I don't know. When I met some guy doing Hopf algebras, he said, oui, Sweedler's dual, but we cannot compute in it. And I said, well, we have a very easy way of a sort of calculus to compute in this. So I will not make the complete review of automata theory because it is at first a whole book in 2 volumes with Samuel Eilenberg, whole book, but there was a part C. I have some manuscript of the part C for people who are interested, and he never published it, of course. And we will see free monoid. And the story of free monoid begins with 2 letters, as Schützenberger used to say. With 2 letters, you have an embedded denumerable-based submonoid, so you can reach the infinity. We will go to this part with base B, which is a very classical division, Euclidean division of elementary school, but saying something to graphically having an insight with regularities. So it is work in progress, but I will present you the beginning for maybe Collatz conjecture and maybe Erdős conjecture. So it is this part is rather work in progress. And if time permits, I will remind how we could solve a small conjecture on the free group and on the what Alain Kuhn calls Fredholm modules on this built on this free group. So the free monoid, so you have the Cayley graph of the free monoid starting from 1 by left multiplication. You have 2 Cayley graphs. Cayley graph with, of course, here you take the letters as a generating set, and you have this Cayley graph by left multiplication. And you see, it will be of importance later that if you compute the outputs, we will see what it is afterwards, level by level, starting from the left, you have a lexicographic ordering between x0, x1 and x1, x0. So we will see why it is of importance. So let us see at once. Okay. I must understand between left and right. Oh. So, yes, but left and right, it is all the drama of words you read from the left. But I don't, this is increasing, and it is increasing, all is increasing. Yes, okay, you have, okay. I understand now. Okay. So, I will indicate at once how it can be interesting to go back to the dream of Schützenberger. He called non-commutative matrices. Of course, matrices are non-commutative, but what he called familiarly non-commutative matrices were matrices with non-commutative coefficients. And he wanted to develop many things about this. And this, you can, for example, consider this differential equation. Here you have I took a classical basis in order to make it familiar, and you have the coefficients. Your series is a series in x0, x1 with analytic functions on omega as coefficients. So you can consider this perturbation of the well-known differential equation for polylogarithm with this term. And with this term, you have still you still produce a shuffled character. Because what? Because this is the specialization. Here is a shuffled character, and the multiplier is a primitive. So it is a very simple calculation. It is a sort of free group of a Lie group. Shuffled characters means that you have S U shuffle V equals SU SV and S1 equals 1. This is shuffled character, and this is infinitesimal characters. That are Lie polynomials or Lie series. Of course, you have an exponential map, and it is a very easy lemma to prove that if it is at one point z0 chosen in omega, if it is a shuffled character, and if the multiplier is an infinitesimal character, it is a sort of tangent map, then the solution is unique, and it can be computed by Picard process, and then the result is a shuffled character.
Excuse me, what is H? Maybe
in a function, maybe. Yeah.
H is it is a perturbation with analytic function as a perturbative term.
And the square brackets is just any function of, or
No,
just commutative? It's commutative.
The bracket is x0, x1 between two letters. X0, X1.
Yes, it.
Sorry, X0, X1 plus minus X1, X0. You have Lie polynomials. It is the first, of course, it is the first example. It is the first example where you reverse, because every Lie polynomial begins in lexicographic order with a Linden word. But I will not dive into Linden words. We have done this so many times in the past in CAP. Here, we just remark that you can compute recursively the iterated integral like that. Of course, if you with cases. What I wanted to, because I am a computer scientist, what I wanted to highlight is, and it will be clear also in the other example of transducer, that states can mean, of course, normal forms and canonical forms, but states can mean also cases. We will see here. So, if you have cases, you can build a transducer with output as an operator. Because this transducer would be too complicated. You can consider the differential system of polylogarithm, which is classical. And here you have three cases, sorry. Yes. Three cases. According the fact that your word is initial, or three cases of recursion. The word begins by x1, the word begins by x0, but there is no 1 before, it is x0 to some power. And the word begins by x0, and there has been an x1. And due to the asymptotic condition here, initial condition, but you can put this on the left, and this can be explained by Lazar elimination also. Due to this, you have to change your lower bound. Lower bound is 0 in this case, 1 in this case, and 0 again in this case. So, so you have some polylogarithms I computed. On this branch, you have a classical polylogarithm, branch of words having x1 on the words of the form x0 to the classical polylogarithm lik equals sum this is equal to li x0 to the k minus 1 x1, because this k is the length of the iterated integral. And what I wanted to highlight is that you can write two states, because you have two cases. The word begins with x0, and you have seen only x0 before, x0, 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 and then you have the output, which is this operator. You take any function, and your lower bound is 1, and you have a transfer edge, and then either you see x0 or x1, your lower bound will be 0. It is not the result is a transducer, which is not so difficult, but it is a transcription, as you will see, that it highlights that you have cases. Your states means cases, and what will be the strength of the star of the transfer matrix is that you can explain the asymptotic, of course, with using the asymptotic condition, initial condition, using, of course, using differential equation. But you can also explain it with Lazare elimination. I will just show you how to do. So this is a transfer matrix. Now, with you can rewrite this. So if you make the star of this transfer matrix, because this transfer matrix is lower triangular, you can eliminate x0, and then you find the asymptotic condition as a term. So I will return to the beginning of my, of course. So we will see the free monoid. We will see also this. This is even more elementary. This is the division in the French, and this will give us the transducer for the Collatz function. And this is the cases are given by partial remainders. 1, 3, 7, 2, 7. You have 1 because it is the 1 here. It can be considered as a partial remainder. 3, 7, 2, 7. And each time, and this is important to do this in the right order, the cases you input the new digit and you output the new digit in the quotient. So, and if we have time, we will see the free group. So last year, Professor Nakamura began his talk with the factorization of words in two variables, non-commutative. So if you factorize it like that, you see that after the last y, you put a bar for the factorization, and the left-hand side is a word in blocks, which is called the code because it is free. The monoid generated by this is free, so you can write it like that. This is the star notation means that you have as much as you want of x's. So this is what we call rational expression in C. It is in grep you have rational expressions, and the plus means at least one. So you see that your factorization is done by this automaton. You begin to read the word from left to right, and here you have all words, including the empty one, of course, because you enter here. At the first, y gives you the second case. First case is you have no y, and if you have the last letter on the right is x, and second case is your word ends with a y. This is classical combinatorics in the word on the words. So this the automaton I was speaking about previously was what we call Boolean automaton. You have just edges and letters, and Schützenberger and Eilenberg had the idea to mix them with flowcharts. With flowcharts, you have a graph with weights or costs, and weights or costs are taken in a semiring, because you just have to comply with the matrix calculation. So you must be able to add and to multiply. And tropical semiring. Tropical semiring, I think, was called. I was hearing when I was a beginner. We were visited by Imre Simon, and I think that at least our school, but it was taken. It had success. it was called Tropical, following to honor this mathematician and computer scientist Imre Simon. I think so, but we can discuss. So the two forefathers I will start from for automata is Samuel Eilenberg, who published these two books, and Marcel Paul Schützenberger, who initiated the story of automata with multiplicities. And in this paper, and it was commutative, and with his school, we developed a lot of commutative, but he was always dreaming that to what he called familiarly non-commutative matrices. So this is a multiplicity automaton. You have initial states that are states with a cost, and you have final states that you go out with a cost. And each time you make a transition, you have to pay a cost. For example, if you start from 2, again, he wanted to change. They were thinking, as well as Eilenberg, that you had the argument first and the function after. And they wanted to change the order of the world, but with no success. In the books of Eilenberg, you can see this. So here, for automata, it is almost a necessity. You start from 2, you pay lambda 1, and you B, C, C, A, B, C, B, C, C, B, C, C.
Second C, go back to 2.
Ah, C, sorry. A, B, C. So this is the path, because it is what we call deterministic automaton. If you have no branch, but you have also automata with, which are not deterministic, with a single letter you can go to 2 states, for example, with probabilistic automata. So due to the left to right reading, you have this. And this is the linear representation, because it is an automaton with a finite number of states. But beware that in their mind, I knew very well Schützenberger and a little Eilenberg. In their mind, automata could be, so we could say finite state automata, but in their mind it could be with a set as a set of states, every set. But of course, the theories are in particular rationality is not the same. So this is the linear representation means that if you due to left to right reading, you have a row, which is of course the states, the initial state is 1 and 2, so lambda 1, lambda 2, lambda 1 at the positions where the states are. This is a column. This is the finite states, and each transition matrix is done as such. You say, oh, I take the state number 1 and I see where it goes. So due to the left to right reading of the world, you have to implement your matrices by rows. So this is mu is used because it is a morphism. So now you see that the behavior of an automaton is a series, and the coefficient of the series is lambda. Lambda is a row. Mu of W is a product of matrix. But they can be what he called non-commutative matrices, and gamma is the column. So you have this, and it is very easy to check that it is this expression that. So you see that we are facing the world of passes, and we have to define what is the star of a matrix. Star of a matrix is 1 plus, this is a star of a series, but a series can have a matrix coefficients. So the star is 1 plus S plus S2. And of course, if R is a ring, we have this. But if R is not a ring, you can just have this positive notation. And the plus notation is starting from S. So now, maybe it is better to, sorry, we will return to Sweedler's duals if we have time after. Skip slide. If you have the generic non-commutative matrix with 2 states, and after you can make recursion by blocks. Let me recall this. Of course, it was very well known by Gelfand and others. Yeah, that and Retag they made the theory of determinants determinants. If you take this matrix, you square it. You have the passes. And if you make the product, you have all paths of length n from 1 to 1, paths of length n from 1 to 2, 2 to 1, 2 to 2. And then you have these formulas for if I have this generic matrix with letters, non-commutative letters, T. So T star equals some. So you have to make the series of all passes from 1 to 1. And it is very, very easy to see that all passes from 1 to 1 are written in simple loops. So what are the simple loops? It is A11, or for each n you have A12, A22 to the n, A21. So it is and every path from 1 to 1 is written in the letters. So you can prove easily that these are independent. So it is it can be called it can be considered as a new alphabet with a denumerable with A11 and A12 A21, A12 A22 A21, A12 A22 squared A21, and it is a new alphabet. So you have this. Similarly for A22, and A12, you stay to 1, and once the last, of course you can have travels, but the last A12, so this is, you stay at 1, and the last A12 you go to 2, and then you remain to 2 because it is the last A12. So this is, and you can compute, and you have all the global behavior of your automaton. Automaton, this series of behavior of the automaton is lambda t star gamma. So if you apply this to polylogarithm, for example, and this you can consider P, Q, R, A, B, C. Now you can consider it as non-commutative. For example, you can consider differential operators in your matrix. You can consider an automaton with differential operators or integral operators, as we saw with polylogarithm, but it was just an example. So, so now, if you consider the transducer of polylogarithm, you have this transfer matrix. Transfer matrix, you could write this because coefficients, as even if they are an endomorphism or integral operator, you can have a structure where they commute with words. So you have a triangular matrix, and then you can compute this with these formulas, but it is simplified by the fact that A12 equals 0. So this is the star of your matrix. And now you can use laser elimination. What says laser elimination? The set of all words taken into account by this representation can be also computed like that, and then you can. This is at least 1x1, and at least 1x1 makes you the integral to be converging, and this is x0. So now, if you compute the whole series of polylogarithm, you can have this computation. This is with laser elimination. These words have at least, oh sorry, for the vertical bar, these words have at least one x1. So this, the limit to 0 is of this part, LE plus, is 1, and then here, sorry, for the limit for 0 is 0, and this is computed by the part with only x0 of your transducer. And if you compute this, with this, you have e to the x0 log of z. So it explains why you can put on the left or on the right of course, you can retrieve it by knowing very well, as Pierre Cartier said. He said, "Oh yes, Drinfeld says it is z to the x0 because he knows very well differential equations, but we did not know so well, so we could not. So what passes in our hand was to use laser elimination. So this, after that, we understood. So I see that time is. I will return to. Yes. So if I go to back to the division by 8 with a transducer, we saw that the transducer can be with you have transitions. You have a command letter, and we saw that this can be non-commutative. So if it is non-commutative, they imagined and their schools afterwards, that you have your input alphabet, and you could put a series with the output alphabet. And what was very well developed and published, and it was only the Cartesian product between input alphabet and output alphabet. But you could imagine that, of course, you could put series and everything. And this is a transducer which explains you the division by 8 in base 10 in order to be at ease. You know, so it is 1, your first partial remainder, it is your first digit. You bring 1, and what you bring will be on the left of the bar, which is the input letter, because they are considered as words. Number will be considered as words in base 10 for this first. And you see that your first partial quotient is 1. And your first partial remainder is 3. So now I bring the 9, and I bring the 9 here, and the output is 4. And then your partial quotient is partial remainder, so is 7. I bring the 4, partial remainder is 2, and output is 9. And so you can, reading this machine, perform the letter-to-letter, because it is what we call a letter-to-letter transducer. If you 11943, so it is 0 because this is no, it is strictly less than 8, 1, 4, 9, 2. So it is a letter-to-letter transducer.
I would say digit to digit. I would say that digit to digit, not letter to letter.
Ah, yes, because Eilenberg called them length preserving, but you have 3 words. Length, digit to digit, if you want. Yes, because they are digits, after all. Okay, let us adopt this here. Digit to digit transducer. What is remarkable, that if you consider, of course it is not remarkable now, but it will be in the next slide, division by 2 in base 3. So I put all the partial divisions. If you start from 0, you bring 0, of course you have 0, and there is a, there is a quotient is 0, and the remainder is 0. If you bring a 1, you are in the 0, because it is a case. You are in the case that your partial remainder is 0. So you, in French, we say abaisser le chiffre. Abaisser. I don't know what it means in English. You bring, when you have the digit, abaisser le chiffre in French means that you have 3, and the 9 is there, so it is elementary school, but ABC, it is, you bring,
you pull it down.
Pull it down, but is it really in is Anglo-Saxon elementary school, is it said like that? Yeah, it's, but, well, we will say ABC, so this is, if you are in the state 0, you bring a 1, you pull it down, as you say, and then you, in base 3, you have 1, so you have 1 and 0 again. But this, you change your case, because you have a partial remainder which is 1. And if you are 0 and you bring 2 and so on, and you get the digit to digit, transducer for division by 2 in base 3. But what is, this is, could be seen as trivial, but what is, we can, if we put outputs in this digit-to-digit transducer, we will get some machine which computes you the Collatz function. What is the Collatz function? It is maybe every one of you know, but I will recall it. If your word, this time it is integer. If your integer is even, you divide it by 2. If your integer is odd, you multiply by 3 plus 1. And the conjecture is for every starting number, it should be end with the cycle 4 to 1, 4 to 1, 4 to 1. And it is still open. Of course, you have partial results and probabilistic. And of course, you can accelerate this function, remarking that if n is odd, 3n plus 1 is even, so you could gain a step in dividing it by 2. So this is a shortcut Collatz function, so-called. So this conjecture says that you end by 2, 1, 2, 1, 2, 1. And the corresponding transducer is just the transducer of digit to digit, dividing by 2 in base 3.
So you should add 1.
Sorry?
You should add 1 in base 3 as well. It's very easy, of course, multiply by 3.
Yes.
Yeah.
So by 2 in base 3, and this is what we call transition structure. So if you forget starting initial states and final states, it is the transition structure is that of a division by 2 in base 3. And now if you, of course, I should have put point empty word. So, but as 1 is used for the digit 1, I cannot put this. I use epsilon, which means nothing. You can concatenate nothing. And here you concatenate 2. And you can compute that the cases are, is your word or odd or even? And if it is, of course, as you have your word, you divide by 2, you have the quotient and a remainder. Remainder is 0 or 1 because you divide by 2. But if you make this simple calculation, is A you see that this computes you the Collatz function. And what is interesting is to, of course, iterate the Collatz function. This is for squared. And for squared, the transition structure, with no surprise, dividing by 2 and by 2 is dividing by 4. So you have to modify. You have to rename your tensor product like that. And so I go to the step dividing by 3, by 2 in 2, 3 by 8 in base 3. So you have this, and you see the regularity. You can bring a 0, a 1, or a 2. You can bring to the state 0, a 0, a 1, or a 2. And very elementary arithmetic calculation, because this it is arithmetic for physics. So, but it explains you that you have a sort of broom at each state. You present 0, 1, and 2. So I present 0, 1, and 2, and then from state 1. I present 0, I present 1, I present 2, from state 2. And you can see that there is a regularity. And this time, if I present 2 in state 2, I have to output one, which is very elementary, but it means that the graph of this transducer can roll like a monodromy, you know, in helix. And of course, this is with the construction is what I said. To every 0, 1, 2, and after, if you change your state, you have to take the non-visited node, and after you count the number of turns you do it, and this is with the output function. But I think I don't have time, so we. How much time I have? Negative time, I think, no? 2 minus 2 minutes, sorry. So I will, my slide will be, and this opens, what is important for this last part, this opens the door to the geometrization of the Collatz conjecture, because this graph has many regularities and many symmetries, but it is work in progress, and such method could be shed some new light. I just indicate, if you have what you call the dagger category, you go to the dual. If you have the division by 2 in base 3, you reverse if you have AB, you reverse it to BA. And you reverse the edges, the arrows, sorry. The arrows and the flip, you flip this, and you get the multiplication by 2. Instead of having division by 2, you get the multiplication by 2 in base 3. And the Collatz conjecture, the Erdős conjecture says that the only piece avoiding 2 in base 3 are for p equals 0, so you have 1, p equals 2, so you have 4, which equals 1, 1 in base 3, and 8, I think it is 1, 1, 1 or something like that, and afterwards, no power of 2 in base 3 avoids the digit 2, and this is still open. There are many advances, but it is still open. Thank you very much. But it was a computer science talk, but I like to bring a bit of, instead of repeating polylogarithm every time.
I didn't follow you. Is the Erdős conjecture the dual of the Collatz conjecture, or no? It's not the same.
No, it is not known. Erdős conjecture. No, it is not. I did not see any paper relating this, but the transducer are dual. But
only the transducer.
But mathematically, I don't know if it is dual. It can be seen.
There's no plus 1 in Erdős conjecture. There's no real plus 1 in Erdős conjecture.
Yes, yes. Yes. It's still open. These two are still open. Very simple, but hard to complete. Thank you.
Thank you.